Hey, hi. We are going to change pages a little bit and look at specific heat capacity, and then we will relate that to solids and liquids, which have intermolecular forces and phase changes. So that will incorporate gases. So let's go ahead and get started, okay? Let me share my screen here and share my screen here. Uh-oh. There we go. Excuse me. All righty then. Okay. I keep doing that. I keep freezing my screen. All right. So what we will be discussing, my friends, is specific heat capacity. Okay. This is a number, and it is a numerical value It is an intensive property. I won't say that. That reflects how quickly, no, how much energy is required to increase or decrease the temperature of 1 gram of a substance 1 degree Celsius. Okay? So it is the energy, that is joules, needed to increase the temperature a degree Celsius, and that temperature increase or decrease will be for 1 gram of a substance. Okay, so we see the units for specific heat capacity as joules per gram degree Celsius. Oops, the joules is the energy needed to raise 1 gram of a substance temperature by 1 degrees Celsius. It tells us how much energy has to be added. Okay, different substances have their unique specific heat capacities. Remember that to use the word substance, it means it's pure. Substances have different and unique to them specific heat capacities, right? Metals tend to have very low specific heat capacities, right? So if you have a low, let's go ahead. The symbol for specific heat capacity is a lowercase c, all right? So if you have a low C, what does that mean? That means you heat up and cool down quickly and without adding or removing very much heat or energy in the form of heat, okay? If you have a high specific heat value, right? I should write the word value up there. Then much, that's supposed to be an M, oops. much heat energy is required to be added or removed, depending on if you're heating up or cooling down. Remember, we don't add cold, we remove heat to change the temp. So it's going to take longer. All right, water has a particularly high specific heat value. Oops. Water has a specifically high specific heat value. And you tell me, who would have a specifically low specific heat capacity? What types of substances heat up and cool down quickly? Metals, right? Metals are excellent conductors of electricity and energy and heat, because those particles are easy to shake, rattle, and roll, right? Okay. There is an equation that you use that can incorporate the specific heat value, the amount of substance, and the change in temperature that we are looking at, okay? And I'm just getting myself some room to write that down. And I will write it right here. And this is your specific heat equation, all right? Specific heat equation. And I think about it like this. This is specific, means it's specific to the gram. Because I say that because up here you have specific heat capacity. There's also something called molar heat capacity. So it would not be specific to the gram here. It would be specific to the moles, which is less specific. So it's not called specific, if you will. All right, the equation is C equals, nope, that's not the equation, it's Q. That is a Q equals MC delta T. That is the specific heat equation. The Q stands for energy, and it is measured in joules. The M stands for mass, and it must be measured in grams. All right. The C stands for specific heat, and it can be measured in joules per gram degrees Celsius or joule per gram Kelvin. Both are interchangeable. I'm going to have to say that so many times. We can talk about why the Celsius scale is the same as the Kelvin scale. It's just the zero is at a different place. So change in temp is your final temp, whether it's Celsius or Kelvin, minus the initial temp. If they have to be the same, but they can either be Celsius or Kelvin. You do not have to convert and then subtract, as you will get the same answer. Okay? So here is your equation, and those are your variables and the units that they need to be in. First question is, what is the specific heat? All right, that means C equals question mark of a substance that absorbs 2,500 joules. That means Q equals 2,500. And because it is absorbed, it is positive. That means adding heat, right? A positive Q means adding heat. A negative Q means removing heat, okay? I should have written that down. That goes right up here, right? Q can be positive or negative. I'm going to write it again. Oops, don't do that, Murphy. Don't want all that mess. A positive Q means you are adding heat, and a negative Q means you are removing heat, which essentially is cooling down. Okay? So you need to be mindful of that. So go back to the practice problem here. Sorry, clean my page up. It absorbs, so that is a positive, and the unit there is joules. So I'm going to write joules down and continue on. When a sample of 100 grams, the mass here is 100 grams. Whoever wrote this did not consider significant figures. You could tell of the substance increases from 10 degrees. So it looks like my temperature initial was 10 degrees, and my temperature final is equal to 70 degrees. Once again, no one's paying any attention to significant figures here. It's rather unfortunate. I would like to put decimals behind all of those. All right, well, I obviously have an MC delta T equation here. My units look good. This is a positive 2,500 joules equals my mass, which is 100 grams. I'm solving for my specific heat. My delta T is 70 degrees Celsius minus 10 degrees Celsius. That is 2,500 joules equals 100 grams times C times 60 degrees Celsius. That is 2,500 joules divided by 100 grams, and 60 degrees Celsius equals C. That is C equals, all right, let's see, calculator. Look at your units too, please, and be sure to show your units in your work. All right, don't skip that part. Show your units. It makes for much better work, much better work. And I see, I'm going to keep 2 sig figs because I cheated and add decimals. Remember when I did that? I can't stand 1 sig fig. 0.42. And you must take note of your units there. That is, as far as I'm concerned, it's wrong, but it will be half wrong. What are the units to this value? Well, let's look. It is joules per gram degrees Celsius. So that's exactly what we'll write, joules per gram degrees Celsius. And that's good because that is an appropriate unit for a specific heat. All right, let's do it again. 200 grams of water, M equals 200 grams, is heated from 24 to 100. T initial equals 24.0. T final equals 100. Better use of sig figs here thus far, except for that 200, never mind. To make a cup of tea, how much heat must be added? Q equals question mark. The specific heat of water is 4.18 joules per gram degrees Celsius. All right, Q equals MC delta T, as is evident by the data we're given. We need Q, 200 grams, specific heat, 4.18 joules per gram degrees Celsius. Change in temp, 100 minus 24 is 76.0 degrees Celsius. Look at there. Look at there. I really chose this just to look at the units. Grams on top, grams on bottom. Those will cancel. And then we also have degrees Celsius on top, degrees Celsius on bottom. Those will cancel. We are left with joules. We were solving for Q. Q equals a big number times 4.18 times 76. I will write 6.4 times 10 to the 4th. And that's joules of energy must be added to raise the temperature of the tea. Last one, not going to do that one. Last one, 55 kilograms, mass equals 55 kilograms, original temperature of 15. There's several tricks here, and specific heat of 0.45 joules per gram degrees Celsius. We need to know the final temp of this metal if we add 450 joules. All right, I've got 2 things to make sure you are aware of. The first one is your mass. We cannot have a unit in kilograms to utilize our specific heat equation because look down here, look down here, our specific heat has grams. So we must first convert our kilograms to grams before doing anything, and that will give us 5.5 times 10 to the 4th grams. And then I see that I need to know my final temperature. So I'm actually going to solve for my change in temp. It will make my math so much easier. No foiling, no long algebra equations. So I'm just going to solve for my change in temp, and then I can apply it and think about what my original temperature was and determine what my final temperature must be, since I know how much it'll change. So this right here is my final goal, right? So I'm going to solve for T. Q equals MC delta T. Q is provided at 450 joules, equals the mass, which is the 5.5 times 10 to the 4th grams. Specific heat was provided at 0.45. That was joules per gram degrees Celsius. And we are going to solve for our change in temp. So 450 joules divided by 5.5 times 10 to the 4th grams times 0.45, just showing all my work. Notice that my, I've got grams here that cancel, right? Top, bottom, I've got joules that cancel, right? Right here. And then I divide, so I get the inverse of my Celsius, and the final will be degrees Celsius. I like to look at my units. 450 divided by parentheses 5.5 with an exponent of 4 times 0.45 close parentheses. That does not make sense at all. It's not much heat, and that is a huge piece of metal. Let me make sure I didn't make a mistake, because I got a very small number. Did you? Okay, that's right. So I'm going to do 450 divided by 5.5 with an exponent of 4. That's a big number, times 0.45. Okay, that's a stupid question. So it's 1.8 times 10 to the negative second, which is essentially 0.018 degrees Celsius. So my temperature is going to go from 15.0 degrees Celsius to 0.018 degrees Celsius. What? 15.02 degrees Celsius. Doesn't make any sense to me. But I don't see any mistakes. So I'm going to move on. If you see a mistake, let me know. I might look at it after class. Object A, or this. This is, we're not doing any math here. We have object A, specific heat of 2.45. Object B has a specific heat of 0.82. Who's going to heat up faster? Specific B, object B will heat up faster. Which object will heat up faster if they have the same mass and equal amount of heat applied to it? It takes less heat, right? It takes less heat to increase 1 gram of the substance by 1 degree Celsius. Right, so it will heat up faster. We have to add less heat to get it to happen. So if we're applying the same amount of heat, this one's going to get there faster. Okay, still a little, that 55 kilogram block, I think, and that's not a lot of heat. So that's why we got such a small number there. Those aren't good numbers. Anyway, I will assuredly see you soon. Take care.